All right, so biology is a science, and so let's talk about what a science is. And the word science actually means to know, and it is a process, and we call that process the scientific method. And then on the left here, you can see we have a diagram of some of the things that go through the scientific method. So the question is, who uses the scientific method? And the answer we typically get are scientists. But reality, it is everybody does. Maybe not quite as structured as this is, but everybody should use it. Unfortunately, in today's society, it seems like science is out the window. Um, and so science is important. And so what I want to do is just kind of go through the process. And we're going to do more of this, especially for our lab section. But again, it means to know, and it's a process where we have questions. And so what I like about the little diagram on the left is it kind of starts what we're trying to do and has some of the steps. And again, I'm going to give you steps, and my steps are structured in the way I think. If you've learned it another way, that's fine. But I want you to kind of get this concept. So I've got it in 5 major steps. I think that works best for me. And so that's how I like to hopefully get you to think about it. But if you have questions on how you've learned it in another course, or it doesn't kind of jive with what you've done, definitely come talk to me. We'll or ask about it in our Zoom session. And we'll try to get that resolved. Okay, so the scientific method. I've got a lot on this slide, and I hate doing that, but I thought it would maybe easier to put it on a single slide for you. What I want you to realize is the first thing that a scientific method does is observation. Often I get people say, "Oh, it's a hypothesis, it's a question." Well, that's not the first step. You have to have information coming in before you can ask the question. All right, so here's what I want. Observation is something that you see, something you taste, something you hear. So it's something from your 5 senses, obviously, but it doesn't have to be something direct. It could be something you read. You might be reading about something and then start to wonder. So literature search, especially in the sciences, it's important to know the background material that's done. And so you're going to be doing a research paper, and you're going to be expected to be able to do a literature search and to use that in your paper. We'll definitely talk about all that in Zoom sessions for labs. No worries. But just want you to realize, so this is going to lead to a question. And that's what a hypothesis is. It's we hear the term educated guess. You take your observations with what you know, you set up a hypothesis. You set up this question. Well, I think it might be because of this. This is how I think it works. Got to know this. The problem with a hypothesis, it's only valuable if it can be two things. One, it has to be testable, and one, it has to be repeatable. A poor hypothesis doesn't pass the muster in a science setting if you can't do both. The testable part is it has to be a question that can be answered, that you can test. And then the repeatable portion is the important part, because if you do it and you say, here's what I did, here's my results, if it's accurate, somebody else should be able to set up the same experiment with the same information you did, the same setup, and get similar results. And if they don't, then Houston, we have a problem. So that's the things we want to take a look at. I want to make a big deal about this. We'll do this a little bit in lab and throughout some of our labs throughout the semester. Is I want you to realize when you set up a hypothesis, there's a null hypothesis and an alternative hypothesis. So if you see H with a little 0 as a subscript, that means null hypothesis. And that means there is no significant difference between one group or another. So for instance, let's talk about COVID vaccines. They've been tested, and there's a couple out that have some effectiveness. And the idea behind this, the null hypothesis is the vaccines successful is if I gave one group the vaccine and another group a placebo, saline water, and didn't tell them, and I still had the same amount of people getting COVID afterwards, that would prove the null hypothesis. There's no difference taking the vaccine or not. Doesn't make a difference. There is no significant difference between the two groups. So my null hypothesis would be correct. The other version of it, the other side of the coin, is the alternative hypothesis. And that would be a large H with a subscript of A. And so and that would be, there's a significant difference. So when you test it, and again, you have your two groups, one getting the vaccines and one not, then you run the test. And the people who are getting the vaccines are getting COVID less than the ones that are getting the placebo, then we would say our alternative hypothesis is correct. And again, under laboratory conditions, the two vaccines that are out from Moderna and Pfizer, both are showing that they are 97-ish, 95 to 97% effective. So that would be the alternative hypothesis on those studies. All right. Once you've come up with a hypothesis, and there can be multiple hypotheses, it doesn't have to just be one. You want to try to make your life easy, especially for the one you'll do, and come up with a single hypothesis, but you set up your experiment. So we're going to give you an example of this during the Zoom. I think it's easier that way, but I'm gonna try to get you, looking at one hypothesis. But for instance, there may be something where, okay, my car, I use this example. We'll do it better in the Zoom session, but birds poop on my car, and the question is why. So I might be able to come up with multiple hypotheses, and so we'll talk about that. All right, so you set up an experiment. I'll tell you the magic sample size is 30. You need at least 30, and that's minimum. My master professor, when I was working on my master's, is how much data is necessary, and the real answer is as much as you can do and afford. The bigger the number, the better off you are. But what we find is the minimum number is 30. One of the things I do when I read papers is I look at the sample size, immediately look at the sample size. That'll tell you how good the data is. There are some sample size studies lower than 30. There are some rare diseases where they don't have that many people. So you work with what you have. But the 30 is not a biological thing. It's a mathematical thing. It's the central limit theorem. And the idea behind it is once you get to 30, it starts to taper off. More data is better, but each new data point doesn't add as much change as before. So 30 is really kind of that sample size minimum number. You want to do a control. You ideally, the control is to make sure that it's just not going to change on its own. So what you do is you'll have one variable different, and so everything's the same except for one variable. The idea behind that then is the variable, if it's temperature, light, whatever it is, that is what's affecting the change. That's not always possible. I shared an office with Steve Tay, who teaches down at down south in Orange County now. He taught at Mount Sac as adjunct as a part-time member when I first started, and a friend of mine. And I hated him. I hate him now. I even tell him because I did field work and he did lab work. And so I did bird studies, which meant I had to be up early in the morning, out in the rain, the cold, whatever weather, and I had no way of controlling any of that. There was no possibility for me to control that. Whereas he worked on hibernation in a squirrel and he did it in lab. They had caught a bunch, brought him back to school, and basically they put him in a refrigerator. That sounds mean. It's not your home refrigerator. It's they would take him down to hibernation temperatures, and so anytime he wanted to work on him, all he had to do was, heat him up. And so he can control all the variables. So what that means is he got his master's done very quickly in like 2.5 years, and it took me almost 4 to get mine. So choose your work wisely. There is a threshold criterion, and that is 0.05. The word significant means not just a difference, but it means a significant difference. And in science, that number has been arbitrarily, and I'm going to tell you it's arbitrary, 95%. We're 95% sure that we're right, although there is chance of an error. And again, we'll see that in lab more, so I'm not going to maybe go over it right now, but we're going to tell you what that exactly means. So we'll go over that in lab. But a threshold criterion, typically 0.05 for most science. I will tell you that criterion can change. And it'll go down to even 0.01 or 0.001, depending on what you're working on. And if it is medical and it's life or death, that number gets a lot lower. You can't have 100 people and say, oh yeah, five of them died, we're sorry. So you will definitely change that criteria. But for basic science, I want you to know 0.05 is the standard. Okay, once you do your experiment, you collect your data, you have to do analysis. It is now all quantitative, statistical testing. We're going to do a couple of statistical tests. Actually, we're going to do several tests this semester. It's just the way we go. Math is an important part. You want to help yourself. If you're a scientist, you take a statistical course. If you really want to help yourself, if you're a biologist, is once you transfer, we don't offer it here on campus. You take a biostatistic or a biometric course. That's statistics for biology. And that was a very helpful course, and take it early. Once I took those courses, it made my life so much easier to understand scientific papers and also kind of how to set them up. So my suggestion is you take them early. And again, we'll talk about that in lab more. Old school, just to go back, old school used to be, science, people got PhDs to study bears. And, today it's all statistical. You take measurements and whatever. Back then you're doing, a study on black bears in California. You go out and, bears are big, bears are black, bears eat berries. Where's my PhD? You turn that in today and you get sent back to middle school. So things have changed. So quantitative. So get used to it. If you're a scientist, that's something you're going to have to deal with. And then you come up with a conclusion. And there's 2 different types of reasoning. There's inductive reasoning. You take generalizations from very specific observations. So you're doing some very specific things, noticing some very, very kind of minute behaviors. Let's say it's behaviors. And then you take that into a more general, this is what kind of these animals will do. Or you do deductive reasoning, where you have very general premises, and then you try to extrapolate or try to pick what you would expect from these organisms. So 2 different ways of looking at things. Okay, couple more real quick things before we end these lectures. One is hypothesis, theory, and law. Are they the same? And the answer is absolutely not. A hypothesis is an educated guess. We mentioned that early. Those are questions you have with what you know. A theory is not. And a theory is a tested hypothesis. Theories don't necessarily need to be true. We want them to be true. But a theory is a tested hypothesis that has a lot of data to support it. And so a theory has a lot of weight to it. Again, it may not be true, but at least it explains what we have and what we know today. The reason I'm going into this, I want to make sure you understand it, is because if you read the paper or the general, information that's out there, the general public uses hypothesis and theory almost interchangeably, and they are not. Hypothesis is a guess. I see that and I go, oh, it's a good hypothesis. Somebody needs to test it. When I see a theory, I'm like, okay, somebody has tested it. I'm interested to see what they've done, and do I agree with their conclusions? It has a lot more weight. The last one is a law, and a law is basically we're pretty sure this is true. We've tested this over and over and over, and we have not found anything wrong with it. The law of gravity is probably a good. If I was to take the computer off this table and I held it up and I just let go, it's going down. I mean, I know that, that. If it ever goes up, I think I'll freak out. but yeah, so that's something that we've tested enough now that we're pretty sure is true. So that would be a law. All right, and then so the last thing I'm going to do now, and then we'll go over it more in the Zoom, is science actually just eliminates possibilities. I want to make sure that kind of sticks in your head, so I'm putting it in the recording. But we're definitely going to talk about this on day one. And so the rest of this I'm going to leave. I'm not going to record on. I'm going to leave you'll have the slides, but I want to talk to you in person about how this works and make sure you understand this concept. So with that, I think I'm going to stop the share. And I will, I am not. I'm coming back. Let me share again. Forgot. So let me pull this back up. I want to skip through. I don't care about these, but I do want to go with, I forgot I have this one other concept I added on here. This is, hopefully you know who this is. This is Charles Robert Darwin. He came up, he did not come up, and this is a misnomer. He did not come up with the idea of evolution. He came up with a way to, a mechanism for it to work, and we will definitely spend third exam lots of time on him and his concepts. But basically, it's nothing more than change over time, and that is the book that he wrote of the origin of species by means of natural selection or the preservation of favored racers. Yeah, and so yeah, we will spend lots and lots of time talking about that guy. So, but here's the last thing I want you to make sure you understand. And I'm not sure it's all that important. Well, I think it's extremely important, or I wouldn't talk about it. But I don't think it's as adamant as it used to be. When I started teaching years ago, and even now you hear that there are people that want to teach intelligent design, or you can call it creationism, in science courses. Not so much at the college level, we get left alone, but definitely at the high school level and below, and definitely in different states other than California. It's been in Florida, Texas, South Carolina. And the idea is we want this other theory taught. And the problem is it's not a theory. Intelligence design or creationism can't be tested, and it's definitely not repeatable. How do you test if there is a higher being, if there's a God, an Allah, a giant pickle? Hell, I don't know what you I don't know what you believe. And so what I want you to understand is why scientists do not want it taught as a theory. And again, it's because it's not. How do you test if there is a God or Allah or the giant pickle? What do you do? I could run out in the front yard during a lightning storm, and God, if you're there, Allah, you're there. Hit me with lightning. I'm not sure that proves it, and all that does is get the police, my neighbors to call the police again. Cooper's out in the front yard running around naked. So I want to make sure this is clear. I'm not saying that the topic itself is wrong. What I'm saying is it's not a question for science. There's no way to test it. There's no way to repeat it. So these kinds of things should be brought up in the religion classes. and with your rabbi, with your priest, um, um, with with your religious leaders. So definitely important, I think, topics. But again, I want to make sure you understand, because it doesn't fall under the idea of what a science is, that which needs to be testable and repeatable. It really is not a question for this class. You want to talk about it off camera, off of in an office hour. I'm more than happy to discuss it. Lots of biologists are religious. A lot of people in our department, and so. But again, not necessarily a question for science in the science class. Okay, I think that's it for it now. Finally, so I will stop the share and I'll stop the recording.